with Unreal Engine 5, we've pushed our signature Gears style to the next level. So let's show you a taste of what we've built. Welcome to the Pay and Save Superstore in downtown Kelowna. In previous games, a space like this was limited to 3 shadow casters in view. With MegaLights, we now have hundreds of light sources, all casting shadows at 60 frames per second on Xbox Series X. This TV display wall utilizes animated area lights with light functions that are driven by the video itself fully on the GPU. They each cast eerie and unsettling dynamic shadows with soft penumbra across the scene. The Pay and Save is a great example of how we've created environments with geometry collection destructible assets like this tiled pillar. These dynamic objects cast and receive light correctly, so destruction stays visually grounded exactly the way you'd expect in the real world. Let's check out the freezer section. All these freezers have multiple area lights inside them to simulate that realistic lighting effect of the frozen food section of your local grocery store. During combat, bullets create a dynamic shatter point in the glass. When it shatters, all the pieces collide with the environment using hardware ray trace collision with physically accurate, translucent reflection. It's amazing to see how many light sources there are in here. There are hundreds of them, from the small lights on Marcus's armor to the large spotlights on the ceiling. There is no way we'd ever be able to achieve this effect or have this many ray-traced area lights on current generation hardware without MegaLights. A staple of the Gears franchise, E-holes are back in Gears of War E-Day. So let's open some up. Without all the monsters in the way, you can see all the volumetrics and smoke lit perfectly. One of the things we're super excited about that was unthinkable in the past is having shadows on every single one of our muzzle flashes. This is a really great improvement that adds to the dynamic combat of Gears with a more believable firing experience that puts you right in the middle of the action like never before. Our game isn't limited to just a single space. We can explore the entire city of Kelowna with tens of thousands of shadow casting lights. Delivering E-Day with this level of visual fidelity has not been easy, but we can iterate so much faster with hardware ray trace Lumen compared to the baked lighting we used in the past. With MegaLights, our lighters are no longer constrained by the number of real-time shadow casters, giving them the freedom to light our game with the same complexity as the real world. And we have 100 times the geometric detail in our assets due to Nanite's micro-polygon rendering.
We didn't want the largest world, but the densest. A city that feels lived in at every scale, where every corner carries history and every surface tells a story. Port Desire is shaped by human clutter, cramped market alleys, layered graffiti, worn stickers on electrical boxes. It's a story with every frame, from a messy apartment where characters go about their lives to the skyline of the city. As a relatively small team, that ambition came with real challenges. We wanted extreme detail everywhere, but we also needed stability and performance without hand optimizing each location. For us, The answer wasn't a single system, but a shift in how we built the world. We prioritized density over scale, and we built a pipeline that let artists handcraft spaces without constantly stripping detail back and without relying on procedural generation. Nanite is what made that approach viable. It lets us keep a high level of detail across surfaces without treating every asset as a trade-off between fidelity and performance. Our custom implementation of FastGeo in combination with the world partition system enables a seamless experience that never breaks. It allows us to have details in every nook and cranny and tell a million small stories. In fact, we have more objects in any given frame than the entirety of the ascent. With this workflow, we can preserve detail and density in every corner, from the smallest bolt on a freighter to the city as a whole, with no invisible walls and no loading. We build tools inside Unreal to help our artists handcraft the entire city, alley by alley, building by building, block by block. To show Port Desire's full range as an urban city overrun with vegetation, we needed dynamic lighting. From the cozy, lush midday sun to the darkest, the most dangerous alleys where even the bright neon light does not reach. The challenge was maintaining a fully dynamic day, night, and weather system without unpredictable frame times. Lumen gives the foundation for fully dynamic lighting, and MegaLights let our artists focus on the believability of the space instead of tuning every single light source. Every believable space needs dozens or hundreds of individual light sources. From the smallest blinking electronic warning light on a camera to the large neon signs above a marketplace. MegaLights allow us to retain the visual fidelity bar we're aiming for while keeping performance considerations low. Once everything is dynamic, it starts to affect the gameplay in more direct ways. Players can shoot out a street lamp, flood a space with a flashlight, or they can leave an area in darkness and have the AI NPCs react to light and shadow, shying away from glare, searching through darkness, or escalating when something feels off.
Let's see who's got the bigger gun, motherfucker!
To make the city feel alive, we leaned on the mass framework to drive our crowds. NPC density and types shift based on time of day, region, and weather. In the slums, a storm clears the streets, but in the more sinful parts of Port Desire, even heavy rain won't slow things down. Mass lets us simulate thousands of characters at once, over 3,000 at any given time, which is also more than the entirety of the ascent. So the city always feels active, no matter where you are. We're also using MetaHuman, paired with our own character randomization system. Together with MetaHuman Animator, we can generate and bring to life thousands and thousands of variations of characters, so that the main characters and the extras in the background are all unique. We wanted a world that reacted systemically to the player, without us having to hand-place effects and destruction. Filling a world of this density and scale with contextual effects while maintaining performance and interactivity was one of our key challenges. By combining PCG and Niagara data channels, environmental effects are procedurally populated where appropriate. Wherever artists place trash or leaves, particles will spawn dynamically based on wind, weather, and player actions. Shoot a bullet or throw a grenade, and particles will move out of the way. We combined chaos physics and their own GPU-driven solution to support tens of thousands of moving objects simultaneously. The result is a reactive environment where smoke lingers, embers drift, and broken glass stays where it fell. Creating NOLA has been the process of finding where the engine ends and our custom tools begin. Achieving this level of density, lighting complexity, and systemic reactivity was previously impossible for a studio of our size. By leveraging UEFN's latest tech to bypass traditional development bottlenecks, we have finally been able to build the uncompromised version of the world we wanted to create for years.
We plan to release in early access at the end of 2027-ish. We know how game dev works around here. However, Epic will be shipping things on the tech stack ahead of the early access release, just to make sure we get it right. 6.0 will be released 12 to 18 months following the early access release, and we expect just about everyone should be able to move their projects to 6.0, as it will still have all of the mainline UE5 tech, except for Cascade, where we're killing that one. That one's not going to make it. So get on the Niagara train. That said, we will be taking the opportunity to make some big architectural and other breaking changes that we wouldn't normally do in a point release, so you can expect a similar upgrade path from UE5 to 6 as we had for 4 to 5. We'll keep everyone up to date on our progress as development continues, and now Curtis is going to come up and give us a more detailed breakdown of the gameplay architecture. Thank you.
Thanks, Marcus, and good morning, everyone. I'm Curtis. I work on the gameplay architecture in Unreal Engine, and today I'm excited to talk to you about the new gameplay framework for UE6, which begins with Verse. Now, Verse is a next-generation programming language, purpose-built to power massive, persistent game worlds at scale. We originally released it 3 years ago in UEFN, where we could grow it to become the foundation for UE6. And Verse draws ideas from functional, logic, and imperative languages, and it should feel immediately familiar to anyone who's worked in languages like C# or Python before. But it also has some unique features aimed at solving the complexity and scaling problems of modern game development, starting with this unique software transactional memory model, or STM. Now, all functions in Verse run as part of atomic transactions, which can be rolled back and re-simulated as needed. And this lets us do a lot of interesting things in our game's code. So for example, to check if an object can be successfully moved in the world, we can simply set its position, then do our spatial queries to see if it's hitting anything. If it is, we abandon the entire transaction, reverting the entire operation, and pretending the code never ran at all. Now, Verse's transactional memory model can also help us address another big problem in game development, building enormous worlds with larger player counts. And today, one of the big limiters to really building larger games comes down to server technology. Scaling a game to run on multiple game servers requires a fundamental rethinking of your entire game's architecture. Well, with UE6, we're working to build a full distributed software transactional memory system to address this. So here's the idea. We take your existing single-threaded style Verse game code, and then we distribute it across multiple servers. When an object's needed in one server, the Verse runtime rolls back the current transaction, migrates the object over to the server, and then reruns the transaction with the object now present. And this is all done in a way that retains the transactional consistency of the original program. And finally, with Verse, we wanted to make saving game data way simpler. So the Verse runtime can automatically synchronize and save any global state for the program, and then share it across all running instances of your game or an ecosystem. And to the programmer, what this means is that setting up something like save state for a player is as simple as setting a single global map of player to save state. No more having to set up databases or coordinate schemas between your game and other backend services. You can do all of this without ever leaving Verse. Now let's take a look at how Verse fits into the bigger UE6 gameplay architecture. So at the foundational level, we have the Verse runtime, along with all the UE systems that exist today, like rendering, chaos physics, meta sounds. With Verse, we're also introducing the Verse scene graph framework. This is a modern game component framework with full support for prefab-style workflows and runtime composition. The scene graph has been designed to utilize all the power of the Verse language, including modeling the entire prefab data model through Verse's type system. Above this, every core system in the engine is exposed as concrete Verse objects. Each material, mesh, Niagara system that you author becomes a type of Verse class with a statically validatable API. This lets us use the Verse compiler to validate all of our data in a unified manner across the entire engine. For example, if you change a parameter in a particle system, you'll immediately know where in code needs to be updated to match. And finally, we'll be introducing high-level frameworks for common game systems like characters, weapons, and vehicles. Now, building with these frameworks helps speed up development, but it also creates content that can be shared widely across games and ecosystems. So imagine grabbing a car from Fab, and instead of simply getting a skeletal mesh and some animations like you might today, you get a fully working Verse module for a car that functions across all of your games. With the UE6 gameplay framework, we're envisioning a world where enormous amounts of code and content is being built and shared between these projects, with Verse providing strong backwards compatibility guarantees to help the ecosystem grow sustainably. Of course, we'll need a place to store all of this code and data, and here to talk about that is Matthias.
Mesh terrain is a new way to author complex terrain without being locked to a height field. And it's more than just a mesh. It's partitioned for collaborative workflows, supports world partition streaming, and is designed to scale across platforms using the same source assets while tuning the runtime representation for each platform using Nanite when available. With mesh terrain, you have full 3D manipulation capabilities. Overhangs, tunnels, floating islands, shapes you simply couldn't build before. And because it's mesh-based, you can also control tessellation at the triangle level. That means adding detail exactly where it matters, while saving memory and performance where it doesn't. As you'd expect, you can paint material layers, but also additional attributes, and it supports virtual texture with automatic UV generation. Mesh terrain uses non-destructive modifiers and procedural tooling, so iteration becomes dramatically easier. Everything can be layered, reordered, combined, and adjusted at any point in time, so you can literally move mountains. It also works natively with PCG and comes with an expanded modeling toolset. But best of all, in our ongoing Fortnite optimization efforts, mesh terrain has a smaller memory footprint and runs faster than landscape. Higher quality, lighter costs, more creative and technical freedom. That's mesh terrain. Another big focus of 5.8 is helping you go faster from idea to result. Performance capture has matured to scale from one operator at a desk to a full mocap stage with control over every recording device on set, including video. And we're taking that further. Earlier this year, Meshcapade joined Epic, bringing world-leading technology for markerless motion capture from video. We've already started integrating it into the ecosystem, and today we are releasing the MetaHuman Animator markerless motion capture plugin on Fab. You can drive a character's body, face, and hands from regular video. No suits, no markers, video in, animation out. For animators pursuing feature quality work, this is our most significant animation release yet. We've made high-end animation workflows more interactive, more intuitive, and more connected to the creative process. From sculpting directly on stylized rigs, to controls that live on the character itself, to a simplified timeline that keeps you focused on the performance. These are the same tools our animation team uses every day, and now they're available to everyone, and we're releasing the sample with 5.8. On the cinematic side, offline depth of field gets a major upgrade. We now render the blur the way a real camera makes it, by sampling the scene from multiple points across the lens. So you get physically accurate defocus, even on translucency and thin geometry. For productions working with ultra-high resolution media, the new tiled MIP-map video format gives you compressed video that holds up at scale. It only decodes the tiles and MIP level your viewport actually needs, so you don't pay to process pixels no one is looking at.
Getting lighting right on Unreal is a skill that means touching dozens of parameters that all need to work together. Light balance, cloud materials, sky atmosphere, post-process. That's a lot to know. But by creating a dedicated lighting skill, you just describe what you want, and the model orchestrates that all for you. Ask for a purple dusk. And there it is. Under the hood, it's adjusting all those settings in concert. Then we can ask for overcast skies. And this is a good example of where the model gets things wrong. It misread the sky and tweaked the cloud material the wrong way. But you can see exactly what happened, correct it in the next prompt, and you're right back to where you want to be. Because models also have real-world knowledge, you can just say, Bogota at 9:30 in the morning. And it will go and figure out the sun position, direction, temperature, and atmosphere that actually matches that. And if you want to match something specific, you can take an image. So here we used one of Vancouver, and ask it to replicate that look. It uses screenshots to assess and iterate until it gets there. And everything is still editable. Grab a road and move it, the city adjusts around it. Ask it to make a building taller or more prominent in the scene, and it does that. But then you can go in and modify any individual asset, making it exactly the way that you want it. This isn't a generated image that you're stuck with. It's a real scene in Unreal, and you control every part of it. Now, let's look at one intersection. We wanted to add a hazard zone, flashing lamps, steam, and a sense of danger as the player gets close. That normally means days of back and forth across multiple disciplines. So here's what we did instead. The warning lamp already has a material, but let's say you want to add something to it. You ask the model to read the existing graph, build the new logic, and insert it right where it needs to go. You can then jump into the material instance editor and tweak the final values by hand. Then you take a Niagara template and extend it, adding a single parameter that drives multiple emitters at once, giving you control over the whole effect in one place. You build out the HUD through prompting in UMG, status display, danger meter, warning states. Then blueprint logic ties it all together. A proximity trigger connected to the material, the Niagara system, and the HUD. Walk in, and everything fires at once. All right, so let's run it. Lamps are off, it's quiet. She walks toward the site, the lamps come on, the steam starts rising. She steps inside, lamps are flashing, steam's pouring in, and the site is erupting. What we've shown here today would take months to build by hand. But with the MCP server and Unreal, our artists were able to make all of this in days. When you lower the technical friction, you can iterate more and make better games. That's what we've built. This is really just a starting point. Bring your own primitives, your own examples, your own skills built around your pipelines. The more your team puts in over time, the more useful it gets for everyone on the project.